Welcome back everyone. In this lecture we will actually see how to prove the defining relation of Möbius function, and then later we will actually see the proof of Möbius inversion formula. So, let us begin by recalling how we defined the Möbius function. So, first we recall the definition of zeta function. So, that is very important in order to define the Möbius function. So, what is zeta function? So, before getting into the definition, let us fix some notation as before. So, we take this P to be finite poset with the partial order less than or equal to. So, this is our finite poset. So, what we are going to do? We are actually going to introduce a linear extension of this partial order to entire P. So, let me briefly outline the proof of why linear extension actually exists. So, then we can fix that linear extension and then work with that. So, what is the definition of linear extension? It is a total order on capital P. So, in particularly we write P as let us say x1 etc. xn, where we actually order them using this total order on this P. So, this x1 being less than etc. less than xn. So, that is the total order. So, maybe I will put tilde here. So, this tilde is the total order. So, now this total order is called a linear extension of given partial order on P if it satisfies the following condition. So, whenever you have xi less than or equal to xj with respect to the partial order that we have it in capital P, that should imply that this I is less than or equal to j in the usual this linear order that we have taken. So, maybe let me use this notation that we have introduced. I have so we say, so let me write it here. We say this less than or equal to tilde to be the linear extension is a linear extension of this less than or equal to if this less than or equal to tilde, that is indeed a total order on P. So, we list this P as x1 etc. xn with respect to the total order as like this, such that whenever xi less than or equal to xj in the original order, that should imply that xi less than or equal to tilde xj in the new total order. So, in this case we say that this less than or equal to tilde is a linear extension of our given partial order less than or equal to. So, now why such linear extension exists? So, that is indeed based on the following fact that any poset has a minimal element. So, any finite poset has a minimal element. So, I am going to leave that as exercise. So, exercise is that every finite poset has at least one minimal element. So, every finite poset has at least one minimal element. Okay. So, now once we have this minimal element, what we can do? We can actually proceed by induction. So, the claim is that this P less than or equal to has a linear extension. So, how do you proceed? We prove this by induction. We prove this by induction on the number of elements inside our capital P. So, now of course, if it has only one element, there is nothing to prove. So, now how do you proceed? You choose a minimal element of this capital P, say this is x 1. So, then what we do, we just remove that element from x 1 from P. So, this P prime is the resulting set by removing x 1 from P. So, now this P dash and this less than or equal to restricted to P dash. So, that is going to be partial order on this P dash. So, this is a partial order on P dash. So, now by induction we know that the cardinality of P dash is exactly cardinality of P minus 1. So, by induction we can actually get linear order on P dash. So, we get less than or equal to tilde on P prime. So, say we list P prime as x 2 etcetera x n with the total order less than or equal to theta. So, now if you add P the x 1 with the P prime. So, then we get x 1 etcetera x 2 etcetera x n. So, now this one actually has this order tilde less than or equal to tilde on x 2 etcetera x n. Now, you just extend this order as follows. You extend that x 1 less than or equal to tilde is smaller than x I for all I greater than or equal to 2. So, now that gives actually an order on P, and you can just verify that this order actually gives a total order on P, which is a linear extension of the original order that we started with. Because by induction we assume that this is a linear extension. So, this is linear extension of less than or equal to on P dash. So, that would say that this new order defined on P is a linear extension. On P. Okay. So, in particularly I can assume that there is always a linear extension of a given partial order on a finite poset, and we need to fix that ordering in order to actually talk everything in terms of matrices. So, like we discussed in the last class. So, that is what we are going to do. So, that is the setup. So, what is the setup? We have a partially ordered set, finite partially ordered set. Let us assume that the cardinality of P is n. So, now what we do, we take a linear extension of this less than or equal to on capital P, and without loss of generality we just denote that by less than or equal to only. So, we then list the elements of capital P as x 1 etcetera x n with respect to that linear extension. So, we fix a linear ordering on P and then write this P equal to x 1 etcetera x n. And since it is a linear extension, so we have that whenever x I less than or equal to x j, that would imply that I is less than or equal to j. So, I am just assuming that the linear extension is given by that 1 less than 2 etcetera less than n. Okay. So, this is the underlying assumption. So, this is the usual order on 1 to n, because any finite poset is actually which has total order on it will be isomorphic to this 1 less than 2 less than etcetera less than n. So, it is understood that what is the linear extension that we are fixing here. So, now with respect to this linear extension we are going to actually work with matrices. So, recall that what is the zeta function? The zeta function is defined to be, so it is a n by n matrix, or it is a function from P cross P to C. Okay. So, either both ways one can actually think. So, it is a function from P cross P to C, or it is actually a n by n matrix. It is n by n matrix over C. So, what are all the entries? So, the zeta of x I comma x j, it is defined to be 1 if x I less than or equal to x j, 0 otherwise. So, that means it is actually an upper triangular matrix. So, when you look at the entries of this zeta function or the matrix. So, let us call this matrix Z. So, what is Z? So, Z is a matrix that consisting of these entries zeta of x I x j. So, it is a n by n matrix. So, this matrix has the diagonal entries 1, because zeta of x I will be 1, because x I is less than or equal to x I. So, since zeta of x I comma x I is 1, so we will have actually the diagonal entries 1, and since zeta of x I x j is 0, if x I is not comparable, but with respect to the linear extension, you can easily see that this implies that I should be greater than j. So, that means the entries that appear below diagonal, so those entries all must be 0. So, all these entries must be 0. So, that means this zeta matrix, so that is indeed an upper triangular matrix with the diagonal entries 1. So, zeta has all its diagonal entries 1, and zeta is an upper triangular matrix. That means the determinant of Z is 1, and that also tells us that Z is indeed invertible matrix. So, this is invertible n by n matrix. So, now what we can do, we can use matrix theory, and then we can actually write down a formula for the inverse of Z. So, let us call this M to be the inverse of Z, and the entries of this is denoted by x I mu of x I x j, where I j varies from 1 to n, and this mu of x I x j we call it as a Möbius function. Okay. The entries that are given by this mu, which is defined from P cross P to C with the property that mu of x I x j, so that forms this matrix capital M. This is called Möbius function. So, this is one of the defining property of Möbius function. That means, we have already kind of very well defined the Möbius function, but what I want to do, I want to spell it out what this means. What is the meaning of M being Z inverse? So, M being Z inverse actually tells us that M Z and Z M, the product of these two matrices must be the identity matrix in n by n identity matrix. So, now we are going to actually just spell it out what is the meaning of M Z being 1 and Z M being 1. Okay. So, that is going to actually give us the defining relations of Möbius functions. So, which I already stated previously. I will state it again, and then we will just work it out the defining relation. So, first actually let us try to understand what kind of function this Möbius function is. For that purpose, we need to understand what can we say about the entries of this matrix M. So, recall that maybe you can take it as exercise, it is not a very hard exercise. Suppose if I have an upper triangular matrix, let us say it is U is coming from n by n complex matrix which is upper triangular. So, recall how the entries of any matrix will be given. So, it is given like this. Here it is A11, A12 etcetera, A1n, and then you have A2n, A31 etcetera, AN1 and so on. So, now if you say that some matrix is upper triangular, if all the entries below the diagonal, so this is the diagonal, all those entries are 0. So, that means this is 0, this is 0 and so on. So, if you write this in terms of actually the matrix entries, so this U which is let us say given to be this. So, then we simply claim that Aij is 0 whenever I is strictly greater than j. So, that is the defining property of an upper triangular matrix. Suppose we have given U such that this Aij is equal to 0. So, and U is invertible then it is not hard to see that U inverse is also an upper triangular matrix. Okay, this is some easy fact one can verify using the definition of inverse of given matrix. So, there are many ways to actually verify this. Either one can use directly the definition and then to try to see U inverse equal to identity. Using that identity, U inverse and U inverse U being identity matrix, one can actually verify this, or otherwise one can actually write down the formula for the inverse of the matrix using the determinant and adjoint of A, and then one can verify directly from that definition that U inverse must be upper triangular matrix. So, now here in this situation we are going to directly verify why the Möbius function matrix, that is upper triangular, and along the way we will also verify what will be the defining property of this Möbius function. Indeed, this is what the defining property. So, we are going to just spell it out. So, let us write down the defining property and then we are going to just verify it. So, let me just recall what is the result that we want to prove. The proportion which gives the defining property of the Möbius function. So, the Möbius function mu satisfies the following. So, if we take all the diagonal entries mu x, that should be 1 for all x in P. So, that is first property, and mu of x comma y, that is going to be 0 if x is incomparable with y with respect to the partial order that we have it on capital P. Okay. So, this is same as saying, okay, this condition you can see that same as saying the inverse of zeta function is again upper triangular, because if x is less than or equal to y. So, let us put it in that xi xj notation. So, if xi not comparable with xj, then that should imply immediately that I should be strictly greater than j with respect to the linear extension that we actually fixed in the beginning. Okay. So, this means the entry mu of xi xj appears below the diagonal in the matrix. So, then that should be 0 because the zeta function itself is upper triangular. So, the Möbius function also should be upper triangular. Okay, but this is something we will actually directly verify without getting into this. So, this is another important defining relation. So, here we have most important one. So, the most important one which says that when we take mu of x y, which can be computed recursively using the following relation. So, which is given by minus summation mu of x z, where z is lying between in the interval x less than or equal to z strictly less than y. Similarly, if we use the other z m being identity, we get something like this. This is same as minus summation mu of z comma y, where z lies in the interval open x and closed y. Okay. And this is the most important relation that actually tells us how to compute Möbius function in terms of induction. Okay. So, these are all the three important defining properties of the Möbius function. Okay. So, let us try to prove this. So, again what I am going to do, I am going to just use the matrix language in order to prove this. So, that means I am going to just use the important information that m is inverse of z. So, let us rewrite everything. So, recall that we have p which is given by x1 etc. xn, and whenever xi less than or equal to xj, that should imply that I is less than or equal to j. So, this is the linear extension that we are working with. So, now we have the equation mz equal to identity. Now, recall that in matrices if we take a product of two matrices, so to look at the ijth entry in the product. So, what we will do, we just take the ith row in the first matrix. So, this ith row, and then we take this jth column in the second matrix, and then we take the entries like this a I1, a I2 etc. a In, and then here it will be b B1j, B2j etc. Bnj. So, then we to compute the entry in the product. So, let us say this is my A, this is my B, the product is C. So, this is myCijth entry. TheCijth entry will be given by the summation Aik Bkj, where k will run over from 1 to n. So, we take this Ai1 and then product with the B1j plus Ai2 and then product with B2j and so on, and then we take Ain, B and j, we get exactly Cij. So, that is the product that we have defined. Indeed, it is motivated from what is called convolution product. So, that is what gives us a matrix product for us. So, we have to just spell it out what happens to m and z in this case. So, recall that z is nothing but zeta of xi xj with ij runs over from 1 to n, and the zeta of xi xj is exactly given by 1 if xi less than or equal to xj, and then 0 otherwise. So, now if I look at the ijth entry in the product mz equal to identity. So, then what we get, the ijth entry in the identity will be delta ij. This is the Kronecker delta function. So, now this delta ij will be given by the summation the entry mu of xi xk, so which is the mik. So, mik, the ikth entry will be mu of xi xk, and then similarly the z of kj is nothing but the zeta of xk xj. So, then we get exactly this zeta of xk xj, where k runs over from 1 to n. So, this is what we get from the identity m is equal to identity. So, now recall that this is going to be 0 unless x I less than or equal to x j. So, that means I can replace this summation by, so this is exactly summation all those k such that x k less than or equal to x j. So, you collect all k such that x k less than or equal to x j, and then you keep this mu of x I x k times 1. So, this is either 0 or 1. So, we are only looking at the terms that survives. So, the delta I j becomes exactly this. So, now it is immediate that if we take x I equal to x j, okay. So, let us if x I equal to x j, so then we are going to look at all the terms in this summation which is equal to. So, okay, first let us claim something about the Möbius function. So, the Möbius function indeed satisfies the property that mu of x I x k is 0 whenever unless x I less than or equal to x k. So, this is the defining property. So, let us make this claim. So, mu of x r x s is 0 unless x r less than or equal to x s. Okay. So, let us assume this claim for time being. So, then what we can do, we can actually rewrite this summation as follows. So, this summation is going to be equal to summation mu of x I x k. Now, this mu of x I x k only survives when x I is less than or equal to x k. So, that will give us that x I less than or equal to x k is already less than or equal to x j, then you have something like this, and this is exactly equal to delta I j. So, now if we work with this equation, what it tells? So, we have delta I j equal to summation mu of x I x k, where x I runs over from x k runs over between x I x j interval. Then from this you can see that easily that if x I equal to x j, then we get 1 equal to mu of x I x I. So, this for example verifies the first equation that we had here. So, this is verified. So, now the third equation again follows by taking x I to be x and y to be x j. So, then this equation tells, and if x is not equal to y, then the left hand side is 0 and the right hand side becomes summation mu of x comma z, where z runs between the interval x and y. So, now this can be rewritten as follows. So, if you keep z being y separately, so then you can actually rewrite as follows: the summation mu of x z, where z runs in the interval between x and y equal to 0 would imply immediately that mu of x y, I am separating this z being y, then plus summation mu of x z, where x less than or equal to z less than y becomes 0, and this is the equation that we have written in the proportion. Mu of x y equal to minus summation mu of x z, x less than or equal to z less than y. So, this is the first part of the equation third. So, this is the first part. So, now the second part again will come from the equation that z m equal to identity. So, this would imply this. So, that is similar computation. So, I will leave it to you to check. So, now let us verify why this mu of x y is 0 if x not comparable with y. Okay, again we are going to use the same equation that we had before. So, recall that we had this first equation just from the observation of zeta function. So, this equation we already had. So, we will just work with that equation. So, delta I j. So, delta I j is given by summation mu of x I x k, where x I x k runs over all x k such that x k less than or equal to x j. So, this is what we have. So, now what we can do, we can just again separate this x k equal to x j and x k not equal to x j. So, that gives delta I j is equal to mu of x I x j plus summation mu of x I x k, where x k is strictly less than x j. So, now we just use induction on j. So, suppose x I not less than or equal to x j. So, yeah, so we are going to work with this equation. So, let me just clear this. If we just take this equation, which is delta I j equal to mu of x I x j plus summation mu of x I x k, where x k is strictly less than x j. So, now by induction on j we want to prove this, okay, and we have already observed mu of so what we by induction we want to prove that mu of x r comma x s is 0 if x r not less than or equal to x s. So, that tells you that x r cannot be equal to x s. So, that part is fine. So, now we claim that this is actually 0. So, now let us look at this x I x j such that x I is not less than or equal to x j. So, let start with this situation. This is the situation that we are interested in. So, now this actually tells immediately that x I cannot be equal to x j. So, that means the left hand side must be 0. So, this gives 0 equal to mu of x I x j plus summation mu of x I x k and x k less than x j. So, now if we are able to prove this part is 0, then we are done. So, to prove that part is 0, we need to say that x I is not comparable with x k. So, x I should be less than or equal to x k, but what happens otherwise? Otherwise, we will have x I less than or equal to x k, but already we have that x k is less than x j, because that is what this equation tells. But these two together would say immediately that x I is less than or equal to x j, which is contradiction to the assumption that x I is not less than or equal to x j. So, that tells that any x k that we have for all x k less than x j would imply immediately x I is not comparable with x j, x k. So, that means by induction we can assume that this part is 0. So, this part is equal to 0. So, now that would imply immediately that mu of x I x j is 0, and this tells you that this mu of x I x j is 0 whenever x I is not comparable with x j. But as I mentioned before, in terms of the matrix, you can see that whenever x I is not comparable with x j, that would imply immediately I is strictly greater than j. Now, since I is greater than j, then mu of x I x j must be 0, because it appears in the lower part of the matrix Möbius function matrix. which is supposed to be upper triangle. So, that proves that the defining relations of Möbius functions, they are satisfied. Okay, so I will stop here with this. In the next class, we will actually see the proof of Möbius inversion formula, and then we will see some immediate applications of that. I will stop here. Thanks.